Solve one problem on composite slab with steady state conduction heat flow with internal heat generation. We will read the given question. A plain wall is a composite of two materials A and B. The wall of material A has heat generation Q is equal to 1.5 into 10 raised to 6 watt per meter cube. Its thermal conductivity is 75 watt per meter Kelvin and its thickness is 50 millimeter. The wall of material B has no heat generation and its thermal conductivity is 150 watt per meter Kelvin and thickness 20 millimeter. The inner surface of the material A is well insulated while the outer surface of material B is cooled by a water stream at 30 degrees Celsius. For steady state condition, first sketch the temperature distribution that exists in the composite. Second, determine the temperature of insulated surface of A and the cooled surface of B. Take convective heat transfer coefficient between outer wall of B and water as 1000 watt per meter square Kelvin. Let us understand the given data with the help of diagram. If we observe the question, wall is made of two composite materials A and B, whose thickness is given. I have constructed three-dimensional diagram. If we observe this diagram from this side view, then we can clearly see the thickness, and if we observe this diagram from the front, then we can see the area. Now we will move for the given data. Here thickness for this composite material A is given. That is, we will use suffix 1 for this composite material A, that is B1 is equal to this 50 millimeter. So standard unit is meter, so we will use 0.05 meter. Now for composite material B, B2 is 20 millimeter, that is 0.02 meter. In the same way, thermal conductivity K1 and K2 is also given for the material A and B. Now one side of this composite material A is getting insulated, so we have to show here insulation. Now there is internal heat generation is taking place in material A. So this internal heat generation, that is Qg. So Qg is given, so we will write here as a Qg. Now what will happen? So one side of this material A is insulated, so this heat generated will flow towards the material B, and this material B is in contact with water, that is fluid, which is at 30 degrees Celsius and which is having the convective heat transfer coefficient H 1000 watt per meters per Kelvin, that is given. Now I will show here the direction of the heat flow, that is towards the material B. So this is the direction of Q. So this direction is important. Now if we observe the question, this material B is having no any internal heat generation. So how to find out the rate of heat flow through this material B? So we will consider the temperature for one side of this B is T, that is the temperature of the line of intersection for this material A and B is T. So we know that heat will flow from this material A towards B and then from material B towards the water at 30 degrees Celsius. Now what is the resistance offered by the conduction process in B? Because there is no any internal heat generation, so we will use the electrical analogy method to calculate the heat flow in B. So resistance offered by the conduction process in B is R1. We will consider here R1. And then after that convection process will taking place, because this area of B is in contact with water at 30 degrees Celsius, and which is having convective heat transfer coefficient. So resistance offered by the convection process we will say R2. Now this heat will transfer in this material B and then towards the water. So one after other, that is the heat is getting transferred. That means R1 and R2 are in series. And what are the end temperature? So starting temperature will be T, because here Q will direction of Q is from left hand side towards the right hand side. So initial temperature is T and final temperature is 30 degrees Celsius. So we have to give limits, that is T minus 30 degrees Celsius. So for this electrical analogy I will write here T minus 30 degrees Celsius, and we will show the resistance R1 and R2 in series. So I will show here. Here is the resistance R1 and here is the resistance R2. So what is the summation of R? Because both are in series, so summation of R is equal to R1 plus R2. Now how to calculate R1? Because for R1 conduction process is taking place. So formula for R1, that is B2 divided by K2A, because this is the thickness B2, conductivity K2, and area is not given, so simply we will use letter capital A. So we will put value 0.02 divided by 150 into A plus. Now for R2 convection process is taking place. So for convective heat transfer coefficient H we have to use for R2 1 upon HA, that is 1 upon 1000 A. Now when we solve this, then we will get the answer 1.13 into 10 raised to minus 3 divided by A. Now how to calculate Q2? So this Q2, because we will write here suffix 2 for the heat flow in from this material B towards the fluid. So Q2 is equal to delta T by summation of R. So delta T, that is temperature difference, is T minus 30. So T minus 30 divided by, we will write this summation of R. Now this A is not known, so we will transfer to the left hand side. So if we simplify this right hand side, then this A will move towards the numerator, and from numerator it will move towards the denominator. So when we solve this, we will get 884.95 in the bracket T minus 30. We will calculate this temperature T. Now this temperature T is the point of intersection in between A and B, where in this composite material A, heat is generated. So we know that the rate of heat generation in A is equal to rate of heat flow in B. So how to calculate the rate of heat generation in A? So for that Qg is given, that is the internal heat generated is given. So to calculate the rate of heat generation, we have to multiply this Qg with volume of A. So how to calculate the volume? Now if we observe, here is the area. So this face indicates the area of this A also as well as B also. Now if we multiply this area with this thickness, then we will get the volume for this composite material A. So I will highlight the material, that is the composite material A, with the help of red marker. So we have to take the whole volume for this. So for this highlighted material, what is the volume? That is this area for this face multiplied by the thickness. So we will take here, that is the rate of heat generation in A. So we will use here the suffix 1 for A, that is Q1 is equal to Qg multiplied by the volume of A. So for the volume of A area, we will use here the letter capital A. So this is the notation multiplied by thickness, that is 0.05. And what is the value of Qg? That is given 1.5 into 10 raised to 6. So if we solve this, then A is unknown. So we will transfer to the left hand side. So Q1 by A is equal to 75,000 watt per meter square. So from this formula, we can say that Q1 by A is equal to Q2 by A. So this Q1 by A is equal to Q2 by A, but Q2 by A is equal to 884.95 into T minus 30. So if we put this value Q2 by A, that is 75,000, then there is only one unknown term, that is T, and when we calculate this T, then it is 114.75 degrees Celsius. So we can take here this value as approximately 115 degrees Celsius. So here is the temperature T, that is we have to calculate. Now we will move for the calculation of temperature at the outer face of B, where for this composite material B is having interaction with the water at 30 degrees Celsius. So for this outer face we will say this temperature will be TBO. Now we have to find out this temperature TBO. Now for this material B there is no any internal heat generation. So we will simply use this resistance R2, and for this outer face this material or this area of the outer face is in contact with water at 30 degrees Celsius. So we can easily take this by using the formula, that is Q2 by A is equal to temperature difference. So temperature difference in between these two faces, that is TBO minus 30 degrees Celsius. Now what is the direction? Direction is towards this right hand side. So initial temperature will be this TBO, and then this is the temperature, that is 30 degrees Celsius. Now in between these two temperature there is the resistance R2 for the convective heat transfer. So how to calculate the resistance R2? So we know that what is the formula for R2, that is R2 is equal to 1 by HA, where H is given, A is unknown. Now this Q2 by A is equal to TBO minus 30 divided by 1 by HA. But this value Q2 by A is 75,000 watt per meter square. That is for 1 meter square the value is given 75,000 watt. So here if I take area 1 meter square, that means area is unity. So we have to put area is equal to 1 meter square, because for this area we have to take this value of Q2 75,000. Now we will simply solve this, or we will simplify this. So 75,000 is equal to 1000 into bracket TBO minus 30, and this area is 1. So there is only one unknown, that is TBO, and this TBO, that is the temperature of outer face of this B, is 105 degrees Celsius, and this is the answer. Now we will calculate temperature at the insulated surface A, that is TAI. Now we know that for this material A there is the internal heat generation, that is Qg. So we have to use the Poisson's equation. So what is the Poisson's equation? D square T by dx square plus Qg by K is equal to 0. So we will first obtain what is the temperature distribution equation. That is, we will use here the equation, or we will develop here the equation in terms of T. So if we observe this equation, here temperature is variable as well as this distance x is also variable. So we will simplify this. So we will integrate this equation on both sides with respect to x. So again it will become dt by dx plus qg by kx is equal to c1, where c1 is the constant of integration. Now I will transfer this qg by k to the right hand side. So dt by dx is equal to minus qg by kx plus c1. I will give here equation number 1. Now again we will integrate this equation with respect to x on the both sides. So t is equal to minus qg by k. Now here x is there. So integration of x into dx, that is x square by 2 plus c1 is there. So for this constant c1 we will write c1x, and again we have to take constant of integration, that is plus c2. So this will be the equation number 2. Now if we observe here c1 and c2 both are unknown terms. Now we have to find out the values of C1 and C2, and then we will put these values of C1 and C2 in this equation, because this is the simplified form, that is T. Then we will get the temperature distribution equation. So how to find out these unknown terms C1 and C2? We will apply the boundary conditions. Now if we observe this material A, then here at this insulated surface, what is the x? Because the distance x is variable. So when x is equal to 0, then we know that the temperature at the insulated surface, that is here this temperature TAI is there, and at the end of this A, that is the end surface of this A, here x is equal to B1 because B1 is equal to 0.05 meter. So we will apply the boundary conditions. So suppose if we take x is equal to 0, and if I put this x is equal to 0 in this equation, then we will get dt by dx is equal to 0, because when we take x is equal to 0, then what is the differentiation for dt by dx? So differentiating with respect to x, that is differentiating with respect to 0, that is equal to 0. Now when we put these two values, x is equal to 0 and dt by dx is equal to 0 in this equation number 1, then here will be 0, here will be 0. So C1 is equal to 0. So now we will get the value of C1, that is equal to 0. Now we will move for the second boundary condition, that is this is the first boundary condition, x is equal to 0. Now when x is equal to B1, so when x is equal to B1, then we know that at this intersection line there is temperature T, and T is equal to 115 degrees Celsius, that we have calculated earlier. So when x is equal to B1, T is equal to 115 degrees Celsius. And we have to consider the previous value, C1 is equal to 0. Now we have to put these three values in equation number 2. So this term will become 0, then we will get one unknown term, that is C2. So T is equal to, that is 115 is equal to minus Qg by K. Now instead of x we have to take B1, B1 square by 2 plus C1 is 0. So this term will become 0 plus C2. So what is the value of C2? So B1 value is 0.05, so 0.05 square by 2. So we will transfer this whole term to the left hand side, so this minus will become plus. So C2 is equal to 115 plus Qg by K. If we solve this, then we will get 1.25 into 10 raised to minus 3. So this is the value of C2. Now this C2 and this C1 is important. So when we put the value of C1 and C2 in this equation number 2, then we will get the temperature distribution equation. When we put the values of C1 and C2, then temperature distribution equation T is equal to minus Qg by K x square by 2 plus, now instead of C1 there is 0, so this whole term will become 0 plus 115 plus Qg by K 1.25 into 10 raised to minus 3. Now we will simplify this. So here Qg by K and Qg by K both are common terms. So we have to refer these two terms. So when I take this common Qg by K, then here 1.25 to 10 raised to minus 3 minus x square by 2, that we have to put in bracket, and here plus 115. Now this is the simplified temperature distribution equation. Now we have to find out temperature at insulated surface. So at this temperature at insulated surface, x is equal to 0. So here instead of x we have to put 0. Now Qg and K values are given in the question. So we will take here temperature at insulated surface, that is TAI is equal to Qg by K into 1.25 to 10 raised to minus 3. So we have to multiply this first term. Then for the second term, if we multiply this Qg by K, then here x is equal to 0. So this whole term will become 0. So minus 0 plus 115. So this Qg by K, if we put the value, then we will get the answer TAI is equal to 140 degrees Celsius. So we will mention here the temperature 140 degrees Celsius. Now if we observe the temperature, so temperature at this first surface or the composite material A, temperature is 140 degrees Celsius. Then as the heat flows towards the right hand side, then the temperature at this intersection line, it is 115 degrees Celsius, and at the outer line or the outer surface of this composite material be, it is 105 degrees Celsius. Now we will join all these temperatures.